Okay, so here we have AP Chem, and this is section 1.1. It's called modeling matter. A lot of it is actually stoichiometry. So for those of you that had chemistry 2 years ago, you should be in pretty decent shape because I guess out of the three of you, all of you took physics. All of you are high functioning enough to figure this stuff out. So we're looking, it says sketch a particulate diagram of each of these. The AP exam makes you sketch a particulate diagram almost every year now. And it's a lot easier than it sounds. So here's what my sketch of CO2 at STP would look like. CO2 gas at STP. So I'm going to represent it as, here's a CO2. Or if you want to be real fancy about it, you can make it look like this. Either one of those. Okay. But for now, I'm just going to do it like this. Here's one, here's one, here's one. And they're also in motion. So like it's got these little blur lines behind it, like a real fast car drawing. And they can go in any direction you want. We're not really limited in number, but the thing you want to remember is that a gas at STP is going to have particles that are really far apart and moving really fast. So for the explanation, so for one thing, it's a gas. So that means the molecules are very spread apart. Lots of room between them. And they are in motion. Which is why we have the tails on them. So that's our CO2 at STP. This next one, SNO2, and it's a solid. Does anybody know what SN is? It's one of the ones that doesn't follow. It's maybe from Latin or something. So, that's SI, that's SE. It's 10.
Oh, sorry.
Like anybody would actually know that unless we looked it up or have used it a bunch. And this is 10-4. 10-4 oxide. I guess if I'm going to go that far, I should explain what I did there, right? So off to the side. Remember that switching of the charges thing? So it would be like this if oxygen was 1 negative, but it's not. Oxygen's 2 negative, which means this needs to be 10-4 plus. That's maybe a topic for later. If we need a refresher on that, I'll do it. I plan on making some specific videos with charges and ionic formulas because that seems like probably the biggest issue that most students have. Okay. And so the structure of this one, let's talk about it first. Is this ionic, molecular? What do you think? Ionic, yeah. It is ionic. And we already talked about the charges, so that's one clue. The other clue is that we have a metal and a non-metal in the same compound. Pretty much implies that it's going to be an ionic compound. So rather than just having little 1 SN and 2 oxygens around, it creates this, what's called a network ionic solid. Like a block of salt is a bunch of sodiums and chlorides all stuck together. I remember the name for it. It was crystal lattice. Weird name. I know, weird name. So here's what it's going to look like. I'm going to I'm gonna make a key for it. Here's my key. So the white circles are going to be oxygen, the dark circles are going to be tin. And this one's not quite like sodium chloride would be. This one, they need a little more space, and so it ends up looking something like this. So this tin has 2 oxygens, and this tin has 2 oxygens, and so on. On the exam, they're not going to ask you to do one that's quite this complicated. Usually it's something like the next one that we're going to do. So I guess a few points. It's an ionic solid. It's a 1-to-2 ratio based on the subscripts. And I guess they have the word lattice in here. This could go on for as long as you wanted. If you had the time and you were very bored, you could make it fill the whole box. It's up to you. Everybody good on this page? All right, so the next one, 0.20 molar what's the name of this thing? Yeah, calcium hydroxide. This is one of our most commonly used polyatomic ions, so you'll catch its name in charge pretty quick if you don't remember it already. Calcium, 2+ charge, hydroxide, -1. We get our CaOH2. I don't remember what year it was, but I've seen an AP question that is pretty much like this. Draw a particulate diagram of this ionic compound dissolved in water. And here's what it's going to look like. So let's make dark ones calcium and light ones hydroxide. And here's what you're going to see. Here's a calcium. So how many hydroxides need to be in here? 2. You need to have 2 hydroxides somewhere in here. And you could go for a second one. You could do another hydroxide, another calcium. Just for the sake of space, I'm going to leave it at this. But it's aqueous. We need to show that it's in water. Now let's think about water. You've got, so here's water. Remember, water's polar. It's got a positive end and a negative end. The oxygen is really electronegative. So it's going to have this negative end, which just makes the other end kind of positive. How is this molecule going to interact with the calcium? Calcium is positive, so the negative part of the water wants to be touching it. And so you end up with something like this. I was at a conference 2 years ago and they described it as Mickey Mouse playing poker. Then we have this hydroxide and this hydroxide. They have a negative charge. And so the positive end of the water is going to want to be towards them.
You have to explain what the water molecules are with like a key with it.
This doesn't. No. And another way that you could do it if you wanted to is you could say, here's calcium 2 plus, and here's hydroxide, and here's hydroxide, but that gets really tight. When you're drawing this, if you clearly identify both of the ions, and then they see Mickey Mouse playing poker, they're smart enough to figure out it's water. And it would be the same for this other hydroxide. And probably two things they're really looking for. One is that they're in the right ratios, 1 calcium, 2 hydroxides. Because that's what the formula says. And the other thing that they're looking for is, does the water point the